Today we delve into the heart of neural networks and explore one such function, the rectified linear unit, or as it's more commonly known, the ReLU function. Imagine a bustling city with traffic lights controlling the flow of cars. The ReLU function operates much like these traffic lights, controlling the flow of information through the neural network. It's a simple yet powerful function that decides whether an input should progress further through the network or be dropped off. So how does the ReLU function work? Here's a step-by-step breakdown. Step 1, the ReLU function gets an input from the previous layer of the neural network. This input, often represented as x, is a numerical value that could be positive, negative, or 0. Moving to step 2, the ReLU function processes this input. It applies a simple rule. If the input is less than 0, it transforms it to 0. If the input is 0 or greater, it leaves it as it is. And that's it! No complex calculations, no intricate formulas. Just a simple rule. If the input is less than 0, make it 0. If it's 0 or more, let it pass. The beauty of the ReLU function lies in its simplicity. It's this simplicity that makes it computationally efficient, allowing it to handle large neural networks with ease. Moreover, it helps the network learn complex patterns by introducing non-linearity into the model. But it's important to remember that the ReLU function isn't perfect. It has its share of drawbacks. For instance, it suffers from a problem known as the dying ReLU issue, where negative inputs can cause neurons to become inactive, thus not learning during the training process. Now, let's summarize the key points about the ReLU activation function. The ReLU function, short for rectified linear unit, is an activation function used in neural networks. It plays a crucial role in controlling the flow of information through the network. The function operates by taking an input x and applying a simple rule. If x is less than 0, it becomes 0. If x is 0 or more, it remains the same. This simplicity makes the ReLU function computationally efficient, but it also has its drawbacks, such as the dying ReLU issue. So, there you have it, a quick dive into the world of neural networks and the ReLU function. Unlike sigmoid and hyperbolic tangent functions, ReLU does not suffer from the vanishing gradient problem. The gradient of ReLU is either 0 for negative inputs or 1 for positive inputs, which allows for better gradient flow during backpropagation and faster convergence. ReLU is considered to be more biologically plausible compared to other activation functions. It mimics the behavior of neurons in the brain, where they either fire, activate, or do not fire based on the input stimulus. During backpropagation, the gradients of ReLU are either 0 for negative inputs or 1 for positive inputs. This means that the gradients do not explode or vanish exponentially as they flow through the network. The stability of gradients helps in maintaining numerical stability during the training process. There you have it. ReLU is more biologically plausible, fast, resource efficient, and numerically stable.